So in the last class, we were talking about the current voltage characteristics and different kinds of currents, such as the light current, the reverse saturation current. And today, what we want to do is to move ahead from there and talk about the current voltage curve or current voltage characteristics for a solar cell, and talk about the different parameters associated with it. Now, this is the formula for the current that you can get from a solar cell. And as we saw before, it's a function of the light current, the reverse saturation current, the voltage across the cell, temperature, and so on and so forth. Now, using this formula, we can draw this current voltage characteristics, this curve that is shown here, which is showing the maximum current to be ISC, or the short circuit current, and the maximum voltage to be VOC, or the open circuit voltage. And you can see the current sort of varies between 0 to the open circuit voltage, and it becomes 0 at open circuit voltage, and we'll understand why that's the case in a bit. Right, so it's sort of a knee-shaped curve that you see here. Now, using the current value for a given voltage, we can also come up with the power curve, which is simply indicating how the power changes as a function of voltage. And power from a solar cell is simply voltage times the current, as expected, right? So again, you can see that the power is 0 at the short circuit current, and also 0 at the open circuit voltage, because at open circuit voltage, the current is 0, and at short circuit current, the voltage is 0. Okay, so in everywhere in between, the power has a non-zero value, and it peaks out at this point shown as PMP, or the power for maximum power. Right, so at this maximum power point, you can also see that the voltage that we get here is what we call as a VMP, and it's smaller than the open circuit voltage. And the current that we get accordingly for it is the IMP, and IMP is also going to be smaller than the short circuit current. Okay, now we focus a lot on the PMP, or the maximum power, because we would want to maximize the power output from a given solar cell. Now, in terms of the other parameters we discussed, well, the short circuit current that we see here in the curve, right, in the current voltage curve, it's essentially obtained when the cell is short circuited. That is, if you connect the positive and the negative terminals, then the voltage across the cell is 0, and the current produced at that situation is what's called as a short circuit current. Now, if we go back to the formula which we just wrote for current, so we said the current within the cell is equal to IL minus I naught times exponential E naught V by KT minus 1. Okay, this is what we wrote. Now, when the potential difference is 0, this becomes 0, and this entire term, exponential of 0 is 1, so 1 minus 1, so this entire term goes down to 0. So what we are left with is we are left with I is equal to IL. Now this I essentially is the short circuit current, because, well, this happens only when you short circuit when you short circuit the cell. So you can say that ISC, or the short circuit current, is equal to IL, or the light generated current. Okay, and that's what we have written here. Now, same way, when we talk about the open circuit voltage, well, if you leave the circuit open, right, if you do not connect the leads, then if you do not connect it to any load, then the current within the current is 0. There's no load current at all, and the voltage you get here is the maximum voltage possible. So this is this is called the open circuit voltage, and this is simply for a circuit which is, as the name says, it's open. Again, how do we get the open circuit voltage? We get it from the same formula here. So for open circuit voltage, I, we said, is equal to IL minus I naught times other things. And here, basically, I is 0 because we do not have any load, right? The circuit is open. So basically what we do is we set IL is equal to I0 times exponential E naught VOC by KT minus 1. And then you solve for VOC, and it gives you this formula right here. Now, again, you do not have to remember these formulas. These formulas will be provided to you. All you need to remember is what are these terms, right? What does VOC correspond to? What is the T here? And as we said before, this temperature needs to be in Kelvin. What is IL? What is I naught? So on and so forth. E naught, as I said, is the charge per electron. It will be provided to you, and K is the Boltzmann constant. Moving on, we always want to maximize the power output. So we said the power from a solar cell is equal to current times voltage. If you want to look at the maximum power, then we will simply have to set it equal to VMP times IMP. All right. Now we can write the power in terms of the voltage IL and I naught in this formula, just because we had the formula for I in terms of IL and I naught as we have seen before. So now this gives me here the power in terms of the voltage across the cell, uh, the light induced current, the reverse saturation current, and the other parameters. Okay. Now let's say I want to find VMP, right? If you want to find out VMP, if you want to find out the maximum load voltage that gives us the maximum power, you can simply differentiate this function for pressure with respect to voltage and set it to 0, right? As you do for finding the local maximum of anything. Now, when you do that, what you get is this equation. This equation is implicit, right? And so if you want to find out the value of Vmax or VMP here, you will have to solve it iteratively. Okay, and then once you get the VMP, then you can calculate the maximum power by simply multiplying VMP to IMP. Now here, what I've written down here, this is what is IMP. Okay, so this again formulas will be provided if you want to make use of this. What I prefer is actually another way of dealing with it. So instead of coming up with these expressions, we can also define parameters A and B such that A is equal to 1 plus ln IL by I naught, right? And B is A by A plus 1. Once we do this, we still have to solve iteratively, but on solving iteratively, we will be able to get the current and the voltage corresponding to maximum power point as IMP is equal to IL times 1 minus A raised to minus B, and VMP is VOC, the open circuit voltage, times 1 minus ln A by A. Now, the beauty of this equation is that we're getting the maximum power point or the current for maximum power in terms of the maximum possible current in the circuit, which is IL or ISC, short circuit current times something. So the something right here, we know it's going to be smaller than 1, right? Because IMP is smaller than ISC. Same way, we are getting the voltage for maximum power in terms of the open circuit voltage, which is the maximum voltage you can get in the circuit, times 1 minus ln A by A, right? So again, this term here, 1 minus ln A by A, will have a value less than 1. And you can simply use this to calculate IMP and VMP. And once you have those numbers, then the maximum power is simply calculated as IMP times VMP, right? So this is what it is. So this is a very convenient way of solving for it. And we will be using this to solve a problem in the next few minutes. Now let's talk about a few more definitions which are relevant to this topic. One is the fill factor, right? So we know that the short circuit current and the open circuit voltage are the maximum current and the voltage you can get in a solar cell. But at these points, at the short circuit current and the open circuit voltage, the power output from the cell is 0, as discussed. Why is it 0? Well, again, power is voltage times current. At ISC, the voltage is 0. At VOC, the current is 0. So if one of this is 0, certainly the output is 0, right? We cannot extract any power at these points, but these points are the maximum current or the voltage we can get within the circuit. So what we want to do is to essentially define a parameter that relates the product of ISC and VOC to the actual maximum power that we can get from a solar cell. And we do that with the help of this fill factor. Now, fill factor, FF for short, is simply defined as the ratio of maximum power from the solar cell, right, PMP, to the product of VOC times ISC, all right? So we do not have any power at VOC or ISC, but the idea of the fill factor is to sort of relate the maximum power we get by the maximum possible theoretical power you could get if the cell was operating simultaneously at VOC and ISC, which it cannot operate by definition, right? So this is just to get an indication of the squareness of the current voltage characteristics, and is a very useful factor when comparing different solar cells. Now, based on our previous definition of A and B, we can simply write, and in fact, the IMP and VMP, we can also write fill factor in terms of A and B as shown here. Right, so this is one very useful way of looking at the squareness of a solar cell. the current voltage characteristics of a solar cell. Now, the last thing we would want to know for a solar cell is its efficiency. It's last, but it's very important, right? And as we do for any solar system, we define the efficiency as the power output, and we divide it by the incident solar radiation. So this is basically the power output in watts or kilowatts, whatever you have, divided by the area of the solar cell times the solar flux, right? The solar flux is written as G. So it can also be in watt per meter square, kilowatt per meter square, however you feel right. Now, if you want to find out the maximum power or maximum conversion efficiency of a solar cell, it's of course the maximum power for the solar cell divided by Ag, right? Which you can replace by this term, or you can write an equivalent terms in terms of A and B. Okay, so that's the end of the theoretical part related to solar cell. Now let's move ahead and solve a problem. Here, we have been told that there's a solar cell which has an open circuit voltage of 0.62 volt, right? So open circuit voltage is given as 0.62 volt, and the light current density, IL by A, is provided as 100 watt, 100 area per meter, ampere per meter square, right? So this is the IL by A, and the saturation current density I naught by A is given as 2.253 in a 10 power minus 9 ampere per meter square. You can see for yourself that IL is much greater than I naught, right? And this is always the case, right? So in terms of the current that you get, the eventual current, it's going to be close to IL, but it will not be equal to IL. Okay, so that's an important point to remember. Now, the other thing is in this problem, just to make it simple, I've given you by symbols again what is light current density IL by A and what is saturation current density I naught by A. Now in an exam, do not expect me to give the symbols, right? I'll just tell you what is the light current density, what is the saturation current density, or something else, and you're supposed to make use of the formulas while knowing what each symbol stands for. Anyway, for this information that is given, we are told that the temperature is 20 degrees Celsius, and we need to determine the load voltage at which the power output is maximum. Okay, so all we need to do is to find out VMP, right? And we have a formula for VMP. The formula for VMP in terms of open circuit voltage is given as shown here, and in this formula, A is defined as 1 plus ln IL by I naught. Now, in the question, we have the light current density, the saturation current density given to us, right? So we can calculate A. And once you have A, along with the value of open circuit voltage that is already provided, we can go ahead and calculate VMP. So it's simply a matter of substituting it, right? So this is the appropriate current densities. You get the value of 25.516 for A. Then you can substitute that in the equation for VMP. The VOC is given as 0.62. And when you do the math, it comes out to be 0.54. So this is the voltage corresponding to maximum power. And as we said, and as we expect, VMP is smaller than VOC, right? Although it's kind of close, but it surely is smaller. It's 0.54. This is the first part of the problem. Now for the second part, for the same cell, of course, we are told that the solar radiation is 770 watt per meter square. So this is the G, right? We need to determine the efficiency of the solar cell if the load voltage is 0.5 volt. So please note this load voltage is different than the voltage we calculated before. The voltage we calculated before was the voltage for maximum power. Here we're not talking about maximum power. We are just saying, okay, this is the load voltage. For this load voltage, what is the efficiency? Okay, so the efficiency is, as we discussed before, power output by area of the solar cell times the solar flux. I could also write it as the power flux or power per unit area for the solar cell divided by the solar flux by G, right? Now, P, as we know, is current times voltage, or P by A is simply current density times the voltage. I'm writing here current density because current density has been provided to us, right? Light current density and saturation current density, although not this current density. So what we need to do is to first find out the current density by making use of these formulas, and we simply need to divide both sides by the area, by the cell area. Now IL by A, the light current density is given 100 ampere per meter square. The saturation current density is given 2.253 into 10 power minus 9. This is a constant. This is another constant, and the voltage V is the voltage across the cell. And here the load voltage is given as 0.5. So this is the number you take. And temperature needs to be in Kelvin. So that's what we do here, 293. right? 293 Kelvin. We were told is 20 degrees Celsius, so you convert that into Kelvin, and it's going to be 273 plus 20. Okay, so that is that is really simple math to calculate. So when you do the math, the current density comes out to be 99.12 ampere per meter square. It's very close to IL, but surely smaller than IL. Based on this, we can calculate the power density as the current density times voltage, which comes out to be 49.56 watt per meter square. Now, once we have this, we can substitute it in the formula to get the cell efficiency as the power density divided by the solar flux, and the efficiency is about 6.44%. Rather small, but okay, it's for the information that we have been provided. Now let's also calculate how much cell area would you need if you want to create a power output, or if you want to generate a power output of 500 watts. Again, at the same load voltage of 0.5 volt. Now for this, all we need to do is, we know that the power output is simply equal to the power flux times the area. Okay, or area is equal to power that you want to generate, which is 500 watts, divided by the power flux for this voltage. Now we already calculated the current for a voltage of 0.5, or the current density rather, and we already calculated the corresponding power flux for it. So all we need to do is to divide the output you want, the 500 watt, you divide it by the power flux for that particular load voltage. What is 49.56? When you do it, you get 10.1 meters squared. So for generating a rather reasonably small power output of 500 watts, we need a reasonably large area, and this is simply because of the low conversion efficiency of solar cell and the low concentration of solar energy itself, right? So this is another part just to give you a feeling for the different numbers that you can expect and when working with a solar cell. So that's the end of the numerical problem. We will conclude this chapter just by talking about what are the emerging technologies, right? So apart from the silicon solar cell that we spoke about, right, which is an efficiency of 20.8, the record cell efficiency to date, that is, with a theoretical efficiency of 33%. We have other technologies which are being worked upon, right? So such as cadmium telluride, CIGS, concentrated PV, quantum dot, perovskite, a lot of different technologies, and each one of them have been demonstrated at different levels of efficiency, right? And they have their own theoretical levels. Okay, so there is a lot of work happening in this field, and in terms of the maturity and in terms of the disruptive potential, this gives a very good overview of where things are. Now, the mature technologies are, of course, the silicon, which is the majority of what we use. It contributes to 90% of all solar PV installations across the globe, 90% or higher, in fact. And then you have the cadmium telluride, the CIGS, which are contributing a smaller, uh, let's say, which are contributing less than 10% put together, right? So CIGS is copper, indium, gallium selenide. It's another material, and it's costlier than the conventional solar cells. There are other things that are happening. There's perovskite solar cells, which has shown potential. There's quantum dot. There's concentrated photovoltaic. So these could be disruptive. This could be take a major share in years to come. We don't know, but there are other options as well apart from apart from silicon-based solar cells. And yes, it looks like there are a lot of work happening in this area, and we'll see how things shape out. But for now, of course, the silicon-based solar cells are doing a brilliant job. With that, we'll end the chapter.